In addition to the larger swap pulleys, I wanted to find out how a modified stock pulley would work with the overrange variator. The pulley I used came on one of my Vento Tritons, and it was modified prior to this project. So far I've only used straight groove torque drivers during the project, but the stock piece uses dual angle grooves. This one starts off at a 44-degree angle, then transitions to a 34-degree angle. The steep starting angle gets RPM up at low speeds, and the lesser angle should keep cruising RPM lower. The grooves on this torque driver were elongated for extended travel, much like what was done to the Morini pulley. The top of the torque driver had to be filed down so it didn't limit movement. The seal was shaved to match. I started out with the overrange belt, but there was a lot of slack in it with a small stock pulley. Takeoff was sluggish even using 1500 RPM clutch springs. I assume this was because of having so much slack in the belt, coupled with a smaller rear pulley. Once it got going, performance felt pretty good. Because of the shift in the torque driver angles and the way RPM settles in combined with delay in my tach, it's hard to tell exactly where RPM is at times. It rose to just over 9,000 RPM, then dropped to 87 to 8,800 RPM the rest of the way to 40 miles per hour. Average time to 40 was 13.12 seconds, which doesn't seem that bad to me considering how long it took to get revs up on launches. RPM increased to 8,800 to 8,900 at 50 miles per hour, with average cruise speeds of 48 to 49 miles per hour. There was a 2.9mm mark left on the variator after reaching 52 miles per hour. Next I tried switching to the bando belt to see if eliminating most of the slack would improve acceleration. I needed to use lighter roller weights to get the best results with a bando. The shorter belt and lighter rollers helped a lot off the line. RPM reached somewhere into the low to mid 9,000 RPM range, then settled down to around 9,000 at 40 miles per hour. 0 to 40 time decreased by more than half a second. RPM progressed to 9,200 at 50 miles per hour. Average cruise speed stayed the same at 48 to 49 miles per hour, but it was less likely to gain speed above average than other combos were. Almost 6mm of travel was left on the variator using the shorter belt. The stock rear pulley did well at speed using an overrange belt, but takeoff was poor. The shorter belt helped at launch, but reduced potential for speed. It didn't really do a bad job for this 50-mile-per-hour rig, but a larger pulley is necessary to make the most of the overrange variator and belt. While I was working with the modified stock pulley, I wanted to see how the Hoka variator would perform with it. The Hoka variator is a Malossi multivar clone that cost about $50. I use it along with a modified rear pulley and a bando belt on most of my builds because it's a cheap setup that has worked well for me. It doesn't require removal of the electric start equipment, so it's better for daily riding in my opinion. I left the starter parts off for all tests during this project for the sake of consistency. The Hoka variator is 97mm, 2mm larger than stock. Hoka makes a 96mm fixed half as well, but I usually save my money and modify a stock fan. Stock fixed halves are usually 95mm and can be reworked to emulate aftermarket parts. In stock form, the drive face has a flat, recessed center. This design moves both faces closer together for an effect similar to a shorter drive boss. It may be beneficial for speed, but low end suffers because the belt can't ride in the center of the pulley. You can add spacers to create more room for the belt, but sometimes spacers have a negative effect on speed and you're left with a flat center section. The middle of the drive face can be filed down to remove the recess. This may allow the pulley to close tighter, but again you're left with a flat center section that's not great for belt travel, grip, or wear. A drive face with a steady angle from the drive boss to the outer edge usually works best. This shape more closely matches the drive belt and lets it ride low in the pulley while making plenty of contact on both sides. The angle affects how the belt travels and how tight the pulley can close at the outer edges for speed. Stock and aftermarket drive faces tend to stay between 12.5 to just over 14 degrees. Greater or lesser angles may not match the belt well, potentially causing slip and accelerated wear. Using too great of an angle can make it hard for the belt to get full travel and speed may decrease. Shallow angles try to push the belt outward more quickly and may make the engine struggle to accelerate. This is not to say you can't go outside the typical range and have favorable results, but sticking with 12.5 to 14 degrees is a pretty safe place to start. If you have access to a lathe, pulleys could be refaced with ease. I'm not that lucky, and paying a machine shop would cost as much or more than buying a new fixed half. What I'm about to show you is how I rework pulleys. It's not exactly the safest method, and I am not suggesting that you use it. I'm only showing what worked for me. Use any techniques and information in this video totally at your own risk. I used an electric drill and a vise as my makeshift lathe, so the first thing I had to do was find a way to mount the drive face in the drill securely. I used an 8mm nut and bolt, a collection of washers, and the woodruff key that locks into the variator fan. I started by placing a washer similar to the outside diameter of the drive boss onto the bolt and putting the bolt through the center of the drive face. Then I stacked a few washers in the hole so they were flush with the center on the fan blade side. Washers closely matching the size of the bolt and the hole reduce play in the assembly. Then I inserted the woodruff key. I've also used a washer that fits the bolt and cutout area with success. Then I added a fender washer and started a nut onto the bolt. I used a ratchet and wrench to tighten the nut and bolt, doing my best to keep it centered. Then I clamped a drill into my vise as securely as I could without damaging the drill. I installed the variator fan into the drill via the bolt. I set up a dial indicator and used it to adjust the bolt in the chuck and the drive face on the bolt until I got low runout readings. A few thousandths of an inch was as good as I could get it. Others have came up with self-centering rigs that don't require so much extra effort to eliminate runout. Once it was centered, I made sure everything was secure again. Then I started the drill, applied WD-40 as a cutting oil, and began reshaping the face with files. I stopped frequently to verify that the drill and fan were still secure. A chunk of metal spinning at a couple thousand RPM near your face is not to be taken lightly. I began by working down the center of the pulley until there was barely a recessed section. Then I focused on making a steady transition from the center to the outer edge. I used a straight edge to make sure I left no major dips or curves. After I got the shape I wanted, I wrapped 220 grit sandpaper around the file and used it to smooth out the imperfections. I ended up with a 12.7 degree angle, the same as the Malossi part I used earlier. The Hoka variator is not only much thinner than the overrange variator, but also uses an 8mm shorter drive boss. That made it necessary to use quite a few spacers in front of and behind the pulley with the starter equipment removed. More importantly, the short drive boss fails to let the belt ride low in the front pulley and high in the rear pulley. I've used many of these variators and I've rarely been happy with them without using spacers on the drive boss. I started without any for this test though. once it settled in around 8,900 RPM, it pulled alright to 40 miles per hour. 0 to 40 times were the worst shown so far at 14.08 seconds average. RPM reached 9,100 at 50 miles per hour and cruise speeds averaged 48 miles per hour. There was a 3.99mm mark left on the variator after going 51 miles per hour. Since the Hoka variator is smaller, that would be equivalent to having 5.24mm left on the Malossi, which is similar to what we saw using the Bando belt with it. Next up, I added 2mm of spacing to the drive boss for a better low-range ratio. RPM increased all around, and I needed slightly heavier weights for the best results. Launches were way better using spacers. RPM peaked around 9,200, then dropped to 88 to 8,900 the rest of the way to 40 miles per hour. 0 to 40 times improved by a full second. RPM was 9,200 or just beyond it at 50 miles per hour with the same average speed as without the spacers. The leftover mark was nearly the same as well. I tried 5-gram weights also, and they dropped cruise RPM by 150 to 200 RPM. It was 0.3 seconds slower to 40 miles per hour, but probably better for day-to-day riding for fast cruising. Using the Hoka variator with modified stock parts was a second and a half slower to 40 and had less speed potential, but I didn't think it did bad for a combo you can get for about $50 that lets you keep electric start. By this point, I had made so many runs with various combos that I thought it would be interesting to find out how a bone stock CVT compared. There isn't much to explain with this one. It's totally stock, aside from tuning parts like weights and springs. The variator measures 95mm across. Some stock variators have a spacer on the drive boss. This one did not, so the belt wasn't in the best spot for takeoff power. Acceleration wasn't as far off from the competition as I expected. RPM climbed above 9,000, then fell to 8,200, and up to 8,500 to 8,600 RPM at 40 miles per hour. 0 to 40 averaged 13.1 seconds, basically the same as the Hoka variator and modified parts. The RPM spread was much greater than other combinations though. By the time it hit 50 miles per hour, RPM was at 9,100 and rose very quickly after that. The stock CVT had a spread of 900 RPM or more up to 50, where others changed by as little as 300 RPM. Average cruise speed was a little low at 47 miles per hour. There was a 4.76mm mark left on the variator after squeezing out 52 miles per hour, equivalent to roughly 7mm on the overrange pulley. I added a 1mm spacer to the drive boss, similar to the washer some have stock, so I had more low-range travel. I had to use 1 gram heavier weights to keep RPM in check with the spacer. To 40 mile per hour performance was almost the same as before. RPM was close, and time increased by 1/10 of a second. I think it got moving a tiny bit quicker off the line, but revved just beyond peak power before shifting and lost whatever it gained. Past 40 miles per hour, there was a big change. RPM shot up to 9,500 by 45, and my max speed was only 47 miles per hour. There was an 8.07mm mark left on the variator. The stock variator just could not cope with a spacer at speed, and even without the spacer it seemed to stop controlling RPM effectively beyond 50 miles per hour. Coupled with the wider rev range, the stock setup did show its weaknesses even though 0 to 40 times were not as far off as I thought they'd be. I had seen a little info about Piaggio rear pulleys being used on Minarelli engines because they were said to match the size of the overrange pulley around 128mm in diameter, and it appeared that they fit with minimal effort. When I tried to find one, everything was from overseas and/or expensive. I suspect there are better sources if you know what to search for, but I was looking at over $100 to get a complete rear pulley. I decided it wasn't worth the money because the whole idea was to find a cheap overrange alternative. Using a variator for $150, the rear pulley over $100, and a suitable belt, the cost would be close enough that an overrange kit would make more sense. Just after I came to that conclusion, a forum member offered me a used Piaggio pulley for $45 shipped, and I couldn't pass it up. The pulley was even larger than I expected, with a diameter of nearly 134mm. Here's the marking on the back of the pulley that may be helpful if you're looking for one. I removed the spring base to see that the torque driver uses multi-angle grooves. They start out around 48 degrees and then transition to near 0 degrees. The pulley slid onto the Minarelli's drive shaft until it hit the edge of the case. I had already removed some material to fit the Morini pulley, but it wasn't enough for this. I marked around the pulley with a permanent marker. Then I used a carbide burr to cut the cases. They were getting thin, so I didn't cut any more than I had to. The pulley fit well and stopped before rubbing the case. I installed the overrange spring and stock clutch without issue. I had read that the clutch bell would need to be spaced out, so it was no surprise when I found the bell made contact with the clutch and pulley assembly. Initially I just used spacers, but later found that clearance under the CVT cover was a problem with the thicker pulley and additional spacing, and the clutch bell left less thread showing on the drive shaft than ideal. I noticed that the threads for the clutch nut stuck out by about 1mm. I ground them even with the top of the nut to eliminate the need for a little spacing. I used the spacer supplied with a Malossi overrange kit and a washer totaling 2.27mm of spacing so the bell moved freely. The next problem came when I tried to fit the CVT cover and it was too small to go over the huge pulley. I centered the pulley on the cover and marked around its edges. It looked like 2.85mm would need to be removed from the CVT cover to fit the pulley. That would be okay at the base of the cover where it's thick, but I would have to cut all the way through the rest of the cover or leave it paper thin. The CVT cover and its driveshaft support bearing are important for strength, so cutting the back half of it out was not a practical option for me. That meant I'd have to downsize the rear pulley to fit under the cover. The Piaggio pulley was too wide at its outer edges to squeeze the 17 to 17.5mm belts I had anyway, and neither would be long enough to travel to the outside of a pulley this large. I decided to cut down the outer half to 128mm. That should make it fit anywhere the overrange pulley would, and the overrange belt that I was using would be maxed out at that point. I used the same trick as I had with the Morini pulley, putting the assembly on the drive shaft so the grinder would rotate the pulley as it cut to keep it round. I started with a grinding disc for quick cutting, then switched to a sanding disc for a smooth finish without sharp edges. Then the cover would slide on, but not all the way. The base of the cover was hitting the fixed half of the pulley that was still 134 millimeters. I ground the base at an angle until the cover would fit over the back of the pulley. Then the cover would slide all the way on, but it was really tight. Closer inspection revealed that the pulley was right up against the inside of the CVT cover. Initially this made no sense to me. If the slightly larger overrange pulley fit, why wouldn't this one? Then I realized that I was using a different CVT cover, because the original broke when I went to kickstart the scooter one day. I grabbed a different CVT cover and it slid on with room to spare. This is one of the things that can be frustrating with Chinese scooters. From talking to multiple forum members and checking out our CVT covers, they range from about 128 to 136 millimeters where the rear pulley sits. Large pulleys will work without issue under some and won't fit properly or at all under others. In addition to the discrepancies in diameter, some covers are also taller. Using the taller covers on some models won't give the primary drive shaft the support it needs, and gearbox bearings fail prematurely. I've experienced this firsthand using short case ATV covers on my long case Vento engines. The only covers I had that would fit were too deep, so I chose to clearance the cover I'd been using. I clamped the cover into a vise and used an 80 grit flap wheel and a drill to remove material. I sanded a little, then checked, then sanded again, and repeated until the pulley made no contact and had just a little room to spare. After that, I tried again to install the cover over the entire clutch and rear pulley assembly, but then the clutch bell was touching the cover. I used grinding stones to gain the clearance I needed. Finally, the cover fit without anything hitting. I assembled the CVT with the overrange pulley and belt. You can see that cutting the pulley smaller had no negative effects using the 816mm long belt. Belt alignment wasn't perfect, but only a few millimeters off. Some setups using direct fit performance parts are this far off. RPM came up to 9,100 to 9,200 off the line, then settled in at 8,700 and pulled to 8,800 RPM at 40 miles per hour. 0 to 40 was the best at this point other than the Malossi kit. RPM reached 9,000 to 9,150 miles per hour, with average cruise speeds around 48 miles per hour. I believe cruise speeds may have been a little lower than the Malossi kits because the Piaggio torque drivers near 0-degree final angles forced the CVT to shift more at speed than my mild engine liked. Belt travel seemed to support this. There was 2.76 millimeters left on the variator from a speed of 51 miles per hour at 9,100 RPM. This pulley worked pretty well with the overrange variator and belt at high or low speed. Since I had the parts right beside me, I tried the Hoka variator and modified fixed half with a Piaggio pulley as well. I installed the overrange belt and used 2 millimeters of spacers on the drive boss to get good low-range travel. The thinner variator improved belt alignment a little. I tried using 2.5 millimeters of spacers as well, but speed and 0 to 40 times weren't as good as this setup. RPM shot up to 9,500, then fell to 8,900 after the shift and climbed back to 9,000 by 40 miles per hour. Average 0 to 40 time was 13.1 seconds, exactly the same as the totally stock CVT. By 50 miles per hour, RPM was at 9,100, and again average cruise speed was about 48 miles per hour. There was a 2.52 millimeter mark left on the variator from a speed of 53 miles per hour at 9,300 RPM, roughly equivalent to a 3.77 millimeter mark on a pulley the size of the Malossi. I gave the Bando belt a chance on this setup as well. It didn't look very promising, seeing how much of the rear pulley was unused with a shorter belt, even with 2 millimeters of spacers on the drive boss. Revs came up to 9,300 RPM, then shifted to 8,500 and up to 8,800 by 40 miles per hour. The runs felt good, but I didn't expect to see a 0 to 40 average of 11.96 seconds. The second quickest of all tests and a quarter second quicker than the overrange variator and belt with this pulley. The major problem was that RPM was over 9,400 by 50 miles per hour. Average cruising speed was 48 miles per hour. There was just over a 4 millimeter mark left over from reaching 51 miles per hour. It seemed strange to get such good acceleration from a belt that couldn't use the whole rear pulley and the variator that produced slower times with other combinations. Unfortunately, I never timed other tunes with it, because RPM at speed was so high if I used lighter weights, or RPM fell too low after shifting using heavier weights. It was a picky setup that needed a very specific tune to be usable at all, and I think everything just luckily worked great together for 0 to 40 runs. Before I put the Piaggio pulley away, I wanted to find out if an idea I had would actually work. I switched back to the Malossi belt with a Hoka variator. Using this combo earlier, revs would rise about 500 RPM above peak and then drop just below it after the shift. My thought was that what would be a less than ideal profile for a fixed front pulley half with a straight groove torque driver may work to reduce the RPM spread with multi-angle torque drivers. Perhaps a flat center section could counteract the torque driver's steep starting angle. While the high angle section of the torque driver resists shifting to raise RPM, the flat center of the fixed half would try to encourage shifting to keep RPM low. It sounded plausible enough to me to be worth trying. I filed a stock drive face until the recessed center was gone and it was flat. Turning the part often helps me to keep it even, since I tend to apply more pressure to the side closest to me. Once it was flat, I taped sandpaper to a sheet of steel and used that to smooth out the filed area. Normally a sheet of thick glass is used to true a surface, but the steel worked well enough for this job. I did put the drive face in the drill just to knock off the sharp edge between the flat and angled sections with sandpaper. I used an extra ½ millimeter of spacing on the drive boss because the flat center section squeezed the belt more. RPM rose to 95 to 9600, then fell to 8900 and pulled to 9000 at 40 miles per hour. 0 to 40 time increased by a quarter second compared to the steady angle modified face. RPM at 50 was the same at 9100 and cruise speed was still 48 miles per hour on average. There was a 2.52 millimeter mark left on the variator after reaching 50 miles per hour. Even though it seemed like the idea had totally failed, I revised the design just a little for one more attempt. I set the drive face up in the drill again and used a file to create a smooth transition from a small flat center to the 14-degree outer area. Then I use sandpaper on a file to smooth out the face. Revs came up to 9,600, then shifted to 8,700 and up to 8,800 at 40 miles per hour. I actually made the RPM spread greater than before, but 0 to 40 times were over 3/10 quicker than the steady angle drive face. Performance above 40 miles per hour remained the same as the first flat center drive face mod. My idea missed the target, but showed some promise for positive results. I still think a steady angle from center to edge will be the way to go for most, but if you enjoy experimenting, you may be able to find a bit of additional performance. Throughout all of the tests, I racked up over 150 miles on the Piaggio Pulley, and even with the strange drive face profiles I tried, belt wear was minimal. I don't see it as a replacement for the overrange Pulley, especially for more race-oriented engines that may have a narrow power band, but it did show potential for street builds. One of the major drawbacks is cost and availability, so if you know of a good source for these pulleys in the US, please share it in the comments.